So hello everyone, welcome to the middle of our Arduino Workshop number 7. So like I said, we're going to go over some different types of motors, how they work, like practically, because when we were working with the H-bridge, we kind of just treated the motor as a black box. You supply current one way, the motor spins one way, supply current the other way, it spins the opposite direction. Here we talk about how they work on the inside. Obviously it's a little less important for when we're like coding stuff, but it's kind of just cool to know. I included a video of how AC motors work, and this is actually like an old school video from World War II that the Army used, but it's still relevant today and it's actually really informative, but we're not going to talk about it today because obviously with robots almost everything is with DC current because we're using a battery, and batteries are always DC current. But if you're curious, you can check out this video. No, we're not doing that. But brush motors are what we just used right now. So a brush motor, the easiest way to tell it's brushed is it has two wires, and as we talked about, you connect one to the supply voltage, one to ground, it spins one way. You swap the wires, it spins the other way. So it doesn't have a polarity. This motor, you see one's black, one's black, one's red. That doesn't mean that the red one always has to connect to positive voltage. You can swap that and the motor will spin the opposite direction. This is what is inside a brushless motor. So there's all these different terms, which I think the video on the next slide will go over in detail, but this is the shaft. This is the part that we actually want to spin. These are windings. These are stator magnets. These are just permanent magnets, which always have a magnetic field in a certain direction. And then we have brushes and a commutator. And so as the video will go through in a second, you'll supply current to the brushes. They'll transfer power to the commutator. Depending on the orientation, it'll create an electric current in these windings, and because they're windings, if you pass current through some windings in a certain direction, it'll create a magnetic field. This magnetic field will interact with this permanent magnetic field, and it'll cause the shaft to spin.
Portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards.
You get that? So current's going to be flowing, it's going to touch from this brush to this commutator ring. It's going to flow this way. As this ring spins, that's not what I want to do.
Rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow
so then
away,
right there, it's
and
switched
on the right side,
to the other
electricity
ring.
will always flow towards.
So the flow is always in
This
the same
ensures
direction.
that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor.
Okay, does that make sense so far?
Yes. Can you repeat what you said?
Yeah, so you see this ring,
Yep.
you're basically supplying current. If you see these arrows, they're kind of hard to see now. There's current flowing this way through the ring to this side. This is positive, this is negative. This ring cuts off here, so when this ring, it's hard for me to visually show when it's on the screen, but when this ring has spun over and now touches this brush, now current's going to be flowing in here through this side, but this side will switch.
Oh.
Trying to figure out the best way to show.
Okay.
Can I like?
You can find DC, and on the right side, electric.
So you notice like this arrow, it's always going to be flowing towards you.
Yeah.
On when the ring part is on the south side.
Yeah.
Embedded YouTube videos are not as convenient
According
as I
to the
thought.
Lorentz law,
So yeah, this
so the
arrow is
coil
always
will
going to be
start to
pointed towards
rotate.
us.
You will notice that as the coil rotates,
So you see on the bottom it's
commutator
pointed away
rings
from
connect
us.
with the power source of opposite polarity.
But
So
now
As
it
a
just
result,
switched
on the
towards
left
us.
side of the coil,
So,
the electricity
So the
will
bottom
always
one's away
flow
from us,
away,
and now it
and on the
switches
right
towards
side,
us.
electricity will always flow towards.
Is north positive? I'm sorry, I forgot.
No, so
Magnet.
this is positive. This is negative. That's the way current's flowing.
Yeah, with the negative one though, like north, you see the magnet right there?
He's saying the polarity in the armature is switching, but those are permanent magnets, so they're not going to be.
Yeah, so these are permanent magnets, and these arrows just show that magnetic field, and then these arrows show the magnetic field generated from this winding. And
Okay.
so this arrow is different than this arrow, so it's trying to move to a position where it's not crossing so many of these lines, and that's why it rotates up. And when it's almost, like he was talking about, when it's almost in the top position, that's when it's crossing the least number of these magnetic flux lines between the two permanent magnets.
But when it's parallel to that magnetic field, it's when it's the least, right? Like the least power. you
Yeah,
have?
yeah. So when it's at the top.
Yeah.
So right
This ensures
here,
that the torque action is also
That's
in
when
the
it has
same
the least
direction
amount of torque.
throughout the motion. So the coil will
sorry, habits don't die quickly.
motion of the rotor if you run such a DC motor.
So yeah, this is how it would look if you only had one ring. So as he's gonna say, we'll just add a couple more
Here
rings.
is the trick to overcoming this problem. Add one more loop to the rotor with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source. So a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation.
So this is more realistic of what a motor would look like if you broke it
In a
open.
practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from...
We're actually gonna stop it here because that covers what we would use for most of our motors. But what he's saying is for bigger DC motors, you want a bigger magnetic field, and permanent magnet motor or permanent magnets can only supply so much magnetic flux, magnetic field.
So it has like a time where it just spoils or rots or something.
Well, what it has is a big coil around the outside that you supply electricity to that creates a bigger magnetic field. And then you have also the electric coils in the center with the switching magnetic field that helps rotate the shaft.
So the motors we use are brushed, and they're using just rocks, magnetic rocks.
Yes, yeah, permanent magnets. Yeah, yeah. If you broke that open, you'd find two permanent magnets. So I think he just talks about like different ways that this can be connected, which is interesting but not really important for us. So yeah, if that made sense, we don't need to really go through this. This just talks about all the components again.
They're called brushes because they brush against the ring.
Yes. Yeah. Yeah, and so for control, we talked about this already. The key is we need to switch a lot of current. Most of our microcontrollers or Arduinos don't switch a lot of current. So we need MOSFETs, transistors, relays, or some sort of dedicated circuit to handle that switching of that much current and a higher voltage level. So some of the pros for brush motors is they're cheap, they're easy to control, they have a high starting torque, which means when you turn them on, the force required to like spin whatever's say like on say we were building a robot with this and we have wheels on the end. When you start the motor, it instantly starts with a lot of torque, so it can spin that wheel. Other motors, maybe when they start, they don't quite have enough torque to start spinning the wheel. So that's good in robotic applications. The cons, since those brushes are always wearing against the commutator ring, which is spinning, they do wear out. So that is a disadvantage. Also, because there's lots of switching when those brushes swing by, or when the commutator ring swings by the brushes.
Little openings.
Yeah, there's a lot of switching going on, so there's lots of electrical noise, and you have a limited top speed. So then, to improve on that, there's brushless DC motors, which these are what the tiny cart uses. Well, any good tiny cart. If you have a cheap RC car, they might use brush motors, but brushless motors are better in most circumstances. So, yeah, the brushless DC motors, this is what they look like. They require an ISC electronic speed controller or another complicated circuit to spin. If we broke it open, this is what it looks like. And so the interesting part, which we'll talk about in a second, but the outside casing is going to be the part that spins. So the outside casing is the part with all these magnets, these permanent magnets. This part is kind of easier to spin than this electric coil, because if you have a good electric coil, it's going to be a lot of wires, it's going to be a lot heavier. This is a little lighter, so spinning this would be easier. Also, because we're not spinning the coil part, we don't need to have brushes. We can run a wire directly to this electric coil and sorry, I'm losing my train of thought. Basically, the spinning part with the electric coil, the electric coil doesn't spin, so you don't need a commutator and brushes to send power to it. You can just directly wire power to it. And we'll talk about how that can work right here.
In order to make the operation more reliable, more efficient, and less noisy, the recent trend has been to use brushless DC motors. They are also lighter compared to brushed motors with the same power output. The brushes in conventional DC motors wear out over the time and may cause sparking. Thus, the brushed DC motor should never be used for operations that demand long life and reliability. Let's see how a brushless DC motor works. The rotor of a BLDC motor is a permanent magnet. The stator has a coil arrangement as shown. By applying DC power to the coil will energize and become an electromagnet. The operation of a BLDC is based on the simple force interaction between the permanent.
So you see, if you energize this coil pair, you're running current through this coil, it generates a magnetic field which flows through it like this. and then you create a north pole over here and a south pole over here. And so naturally you'll see the south pole is going to be attracted to this north pole is going to be attracted to the south pole, and you'll see how it like wants to spin.
The operation of a BLDC is based on the simple force interaction between the permanent magnet and the electromagnet. In this condition, when the coil A is energized, the opposite poles of the rotor and stator are attracted to each other. As the rotor nears coil A, coil B is energized.
And I said that wrong. I made it sound like the coil is the part that spins, but because this is brushless motor, it's actually this outside ring with the permanent magnets is going to be the part that spins. So this south end tried to line up with this north end, but now that it's lined up, you won't be able to spin because it's locked. But if we turn this coil off and we turn this next coil on, now this is north, this is south, the outside ring is going to want to keep spinning so that its south magnetic field can line up with this north magnetic field.
As the rotor nears coil B, coil C is energized. After that, coil A is energized with the opposite polarity.
So now we've gotten back in the original position. The north permanent magnet was on top and the south was on bottom. Now it's switched. The south is on top. So this next A coil should be turned on, but if we actually swap the current direction that's flowing, it'll swap the direction of the magnetic field. So now, I think last time this side was south and this side was north when we passed current one way. We're passing current the other way. Now this is north, and so this south permanent magnet will rotate towards that. And over here you can see over time the order that you need to energize A, B, and C to make the motor spin.
Process is repeated and the rotor continues to rotate. A humorous analogy to help remember it is to think of the BLDC operation like the story of the donkey and the carrot, where the donkey tries hard to
Not
reach
the best
carrot,
analogy.
but the carrot keeps moving out of reach.
And this graphic is priceless.
Even though this motor works, it has one drawback. You can notice that at any instant only one coil is energized. The two dead coils greatly reduce the power output of the motor. Here is the trick to overcome this problem. When the rotor is in this position, along with the first coil, which pulls the rotor, you can energize the coil behind it in such a way that it will push the rotor. For this instant, a same polarity current is passed through the second coil. The combined effect produces more torque and power output from the motor. The combined force also makes sure that a BLDC has a beautiful constant torque nature. With this configuration, two coils need to be energized separately, but by making a small modification to the stator coil, we can simplify this process. Just connect one free end of the coils together. When the power is applied between coils A and B, let's note the current flow through the coils. It's just like the separately energized state. That's how a BLDC works. But you might have some intriguing doubts in your mind.
Alright, so this seems pretty cool, right? And we don't have brushes, we don't have a commutator ring without the sparking. But what... Do any of you guys see a potential problem with this?
Not all the coils are turned on like you said.
Well, he said you can fix that by turning on two at the same time to help kind of push it. So, and this is the north pole. This coil can turn on to north to repel it. This coil can turn to south to attract it. And so now 2 out of 3 coils will always be on.
How do they always know when to turn on which coil?
That is the big problem with brushless motors. Not a problem necessarily, but something that has to be overcome. So with the commutator ring and the brushes, you always supply current in one direction, and the commutator automatically will switch it the way it needs to be switched for the motor to spin. And that's why it's relatively easy to control. You just supply current to one side and the motor will spin. Here, you have these 3 coils that need to be turned on and off in a very precise manner at precise timing to make the motor spin. And that's why, as like Andrew likes to say, brushless motors are actually cheaper, but the controls are a lot more expensive. It's a lot more complicated. So I think he's going to talk about how you
How do I
control
know
it.
which stator coils to energize?
Yeah.
How do I know when to energize it so that I will get a continuous rotation from the rotor? In a BLDC, we use an electronic controller for this purpose. A sensor determines the position of the rotor, and based on this information, the controller decides which coils to energize. Most often, a Hall effect sensor is used for this purpose.
So a Hall effect sensor will just sense the presence of a magnet. It's a simple sensor that will output 0 volts if there's no magnet, and output 5 volts if it's a 5-volt sensor, if it senses the presence of a magnetic field.
Well, isn't it always? Wait, actually, where does that go?
Let's see where he puts it. So it's attached to the
The
outer ring.
BLDC design we have discussed so far is known as the outrunner type. In-runner BLDC design is also available in the market.
Let's see, I think I talk about...
In order to make the
Yeah, I talk about that in a second. So this talks about how it spins. I think this kind of made sense for everyone. With like these 2 coils, if you provide a path, this is going to be north, this is going to be south. The north side is going to be repelled by this and turn towards the south, and then you'll just switch the 2 coils that are turned on. You'll spin the motor. It's the donkey chasing the carrot. So the 2 methods of determining which coil is turned on and off is either using Hall effect sensors or using back EMF. So the Hall effect sensors is this H1, H2, H3. And what it can do is it can sense that this is the permanent magnet. H1 senses that it's north. I don't know the best way to talk over this, but using these Hall effect sensors that can sense the presence of this magnetic field, they're placed in a certain position. So when they sense that, they know, okay. And because in this example, notice how these are like 60 degrees apart from each other, but each of these are no, these are 120 degrees apart from each other. These are 90 degrees apart. So only one of these will like sense the North Pole at a time, and it'll be able to tell the precise position of the permanent magnets. And then, okay, if the north magnet is right here, then I know I can turn this coil to in and this coil to south to make this spin to the next coil. So that's one way to do it. The back EMF, the one coil that's not being energized will be a coil that is sitting there and a moving magnetic field running through it. And based on a moving magnetic field moving through a coil will generate an electric current, and so you can actually measure that current and estimate the position of the magnet. So that's the other way to do it. Luckily, we don't need to worry about that. That's all handled by the controller. None of us are actually going to build a brushless electronic speed controller, unless you guys are really ambitious. But yeah, let's not do that. So for the tiny cart, you probably have seen these before. These are the ESCs. You supply power to it. These 3 wires go to the 3 wires from the brushless motor, And then these 3 wires are the control wires. One's 5 volts, one's ground, and then one's a PWM signal to determine the speed and rotation of the motor. So the pros is there's low wear, there's high speed, high efficiency. The cons, very expensive, complicated to control. Because of the high RPM, if you wanted to connect it to a motor, or if you want to make it spin a wheel to drive a car, for example, you would normally need some sort of gearing to reduce the speed. I don't know, in most of the tiny carts, is there gearing?
Yeah.
Okay.
They all either have a gearing or a straight transmission.
Okay. Yeah. So that's not really a huge con. It just might mean that when you buy the motor, you can't couple a wheel directly to a motor, expect it to drive a car. It's going to spin way too fast and not have enough torque to actually carry the car. Yeah. So the servo is the thing that we're actually going to control. Hopefully we have enough time to do that. We have a little bit of time. So the servo has 3 wires, very similar to the ESC controller. One's 5 volts, one's ground, and one's the PWM signal. I guess the 5 volts is, for most servos, it's either 5 or 6 volts. You can connect them to 6 volts and they'll get a little bit more power. If you only have one servo, you can probably connect it to your regulated 5 volts supply and get away with it. But typically you'll want a separate supply for the servo, because this is going to be driving maybe more power than your Arduino can output. So you might need a separate 5 volt regulator to power this. But this is what's on the inside. A servo is basically, I don't know if you guys have worked with servos before. The advantage of a servo is it doesn't just spin continuously. It's you tell it an angle to point at, and it'll spin until it points in that direction. Let's see. Take this out and never be able to put everything back together, but here, do you have your servo available? So this is a servo. This is the control wires. The red wire is that's 5 or 6 volts. The black wire or brown wire is ground. The orange wire is the control. The PWM signal will send from the Arduino. And then this bag, you got little arms that connect to the end of it. So if you connect this in and then you spin it with your hand, you'll notice this one spins all the way. You're not supposed to do that. I wonder if these are continuous servos. Alright, well, let's pretend it didn't do that. It will normally spin 180 degrees. Well, yeah, I'll test that one in a second. And so if you send it like a 0 PWM signal, hypothetically it'll be all the way on the right. You send it our PWM signal for the Arduino ranges from 0 to 255. So 125 is about in the middle. So if you send it 125, it'll point straight up. And if you send it 255, it'll point all the way to the left. So when you send that signal, it's going to rotate pretty fast to the desired position and then stop and hold it. So this isn't for spinning a wheel and driving a robot. This is for precise control of something at a certain angle. So this is ideal for steering, which is what they're used for, like on the tiny cards. So in this picture, you can see inside there is actually just a DC brush motor. There's all these gears to help reduce the speed And then there's this potentiometer. You guys remember we've worked with the potentiometer before. When you spin it, it changes resistance. So that's kind of a sensor that can tell where the arm is pointing. So say the arm's all the way on this side, the potentiometer is going to be a very low resistance. The arm's all the way over here, it's going to be a very high resistance. And then that information goes to this controller, this small microcontroller built in there. And you'll send it a signal like, I want to be at 90 degrees. I want to be straight up. And the controller takes that information and the information of the potentiometer. Maybe it's a very low resistance. Okay, you're pointed all the way to the right. And then it'll change the speed of the motor. And as you get closer and closer to 90 degrees, it'll recognize, okay, the resistance is increasing. I know at 50% resistance, I'm pointed straight up. I'm at 40 resistance, I'm going to slow down a little bit. I'm at 45, I'm going to slow down any more. Okay, I'm at 50, I'm going to stop completely. And it stops pointing straight up. Does that make sense?
Yeah.
Okay. So that's how it works on the inside, but from a control perspective, we just need to send it a PWM value, and it'll spin to our desired location. So this is what we're going to wire up, and then we'll code it real quick.